All right, this is lecture number 6. One is still doing position analysis with equations, trying to obtain equations to describe the positions of various links as function of the input, uh, the motion of the input link, if you like. And we are still doing trig, and I have an example here for you. So let's look at this linkage. So I have like a rocker, and there is here crank with length R2, and maybe I can also have a little, I'll just change the color, I can have another a slider attached here this end. So right, and this is the locus of the slider. So if this point is A, this here is B, this is C type thing, and I have this angle is theta 2 of this link, which is the crank, right? Uh, this is link number 2, so this the slider will be link number 3, and this here will be link number 4, and this will be link number 5, and this slider is link number 6. So how many degrees of freedom I have over here? Let's just quickly check our degrees of freedom. So in number of links, that's an example here. So we have 6 links, and we have how many review joints? We have the review joint here, and we have this review joint here, at the pivot of the crank. So that's 3 at B5 and at C and B4 and at C5. So we have 5 review joints, and we have 2 prismatic joints, one at A and one at C. So if I calculate my degrees of freedom, I get 3, 6 minus 1, minus 2 times 5 minus 2 times 2, which gives me 1. So I do have 1 degree of freedom. So it is at this stage, I'm now confident that with the knowledge of theta 2, so at any given value of theta 2, I should be able to describe or to perform a position analysis for my linkage. Now, in terms of position analysis, what I'm trying to do, so I'm trying to find the angles and the positions of different links. So my links here, so this is link 3. Here I have a slider, that's a link. Don't forget, we count the slider as a link. We try to find the position of the slider. So this distance from here to there is going to be a variable distance, and I need to calculate it. So whenever we have a slider, this distance here, right? So this distance here is this is a variable. I need to calculate this distance. So I'm going to call this distance R3. So that's R3. All right. So when for a slider, I always part of what I calculate for position analysis is the location of the slider on the link on which sliding takes place. So this distance is R3, and that's a variable, of course. And I have a constant R1, this distance is constant, and R4, the length of link number 4, that's constant. It is like from here, O4, if you like, pivot of 4 to B, that's constant R4, and R5 is also constant. So there's only constants. So what I need to find would be, I need to find the angles of theta for the angle of link number 4. That's a variable, that's function of theta 2. I need to find R3, that's function of theta 2, that's function of theta 2. I need to find possibly also this link changes its angle, so I'll just call it theta 5. This will be function of theta 2. I need to find the location X of this slider, this will be a function of theta 2. So I have like 4 things I need to calculate as function of theta 2. So my input here is theta 2. My outputs would be R3, would be theta 4, would be theta 5, and would be x. All right. So those, all of them should be function of the single degree of freedom I'm dealing with, which is theta 2. So let's try to find our way through this example. All right, so now I can find from this triangle here, small triangle, I can write an expression for R3 straight away. If I say R3 squared is equal to R2 squared plus R1 squared minus 2 R1 R2 cosine the angle between the two sides, which is 90 plus theta 2. If I wanted to simplify the expression for R3 a bit, I'd go R3 squared is equal to R2 squared plus R1 squared, and then when you expand the cosine, you get cosines multiplied together minus sine multiplied together. So I have minus sine theta 2. So this will give me plus 2R1 R2 sine theta 2, and that's an expression for R3, and as you can see it is a function of theta 2. All right, so this was one of the things I was trying to find, was R3, and also because it's a position of the slider, right? That's why it is important, and it's part of the position analysis. Another link whose position is theta 4 is a link R4. Let's find an expression for theta 4. So theta 4 is expected to have values in this quadrant, in those two quadrants, like Q1 and Q2. So you expect theta 4 to fall in here. So theta 4 will be in this quadrant here. This will be theta 4. So if I use cosine function, I should be okay with theta 4. So let's find an expression for cosine the theta 4. So one possible thing, if I take just this angle here inside the triangle, is equal to pi over 2 minus theta 4, then I can say sine this angle divided by R2. Okay, let's do that then. Let's say, but for theta 2, I actually want the cosine. This will give me cosine because sine this angle here will give me a cosine. So if I go sine pi over 2 minus theta 4, right, this angle here, this divide this by R2, this will be equal to sine pi over 2 plus theta 2, divide this by the corresponding or the opposite length or side, which is R3. All right, that's okay, that's a variable. All right, so sine, again, when I expand this here, I get sine 90 cosine theta 4. So this will give me cosine theta 4 over R2 being equal to, again, sine 90 cosine. So it will give me cosine theta 2 over R3, and hence cosine theta 4 will be equal to R2 over R3 cosine theta 2. All right. So this will be, if you want to expand this, if you like, you can go to R2 cosine theta 2 over R3, which is R2 squared plus R1 squared plus 2 R1 R2 sine theta 2. So that's a nice and closed form function which relates theta 4 or calculates theta 4 as function of theta 2. And as I said, because this function will always fall, I mean, the value of theta 4 always falls on those two quadrants, so cosine will give me like a reasonable um, number for theta 4, right? Cosine, if I use cosine minus 1, I'll get theta 4 without a problem. All right, so now I have an expression for theta 4. That's my second thing I was looking for. How about theta 5? All right, so theta 5 now, to move into theta 5, I get out of those triangles, and possibly if I take this distance here, expect this distance to be fixed. That's constant h will be given distance from the pivot O4 to the path of the slider type thing. So this is fixed. So now if I say for theta 5, this theta 5 also is expected to fall in the first quadrant. So if I get cosine or sine theta 5 with this sort of design, I should be okay. So, all right, so theta 5, I need to find the expression for theta 5. So if I decided to project R4 and R5 on H, now I'm doing projection that's similar to vector analysis a bit. So I can say H is equal to R4, right, sine theta 4 plus R5 sine theta 5. Now, because now if you project this here in the vertical axis, you use sine theta 5. So this is R5 sine theta 5, and this distance here to the bottom end is R4 sine theta 4, right? Okay, this gives you an expression for theta 5 if you like. So you can say sine theta 5 is equal to h minus R4 sine theta 4 over R5. And this should be an okay expression for theta 5, because if you do sine minus 1, you get it, because I expect theta 5 to be in the first quadrant with this sort of design. So sine should produce the value for me if I want. Now, if I wanted to get an expression for x, now I use the horizontal projection of the two vectors I just used. So like if I project R5 on the horizontal axis, I'll use cosine, and R4 I'll use cosine, and they both add up to x. So that my expression will be x is equal to R4 cosine theta 4 plus R5 cosine theta 5, and this gives me the expression for x, and I can just get cosine, like finally I can use it like that, and then when I calculate the angle theta 5, I go sine minus 1, whatever this expression here, I go sine minus 1, and then theta 5 I can plug it in here to find an expression. So I have a procedure more than anything. But well, another mathematically initiated students would think, okay, I can get rid of theta 5 completely when I'm calculating theta, when kx sort of thing. I can do that. All right, you can if you decide to call this equation 1 and you call this equation 2, and you can solve them together and get rid of theta 5, because you have sine and you have cosine, and you can get rid of theta 5. Well, I can possibly help you do that, or give you a hint onto this, because we'll do this also a fair bit later on. So if I say over here, write this expression as R5 sine theta 5 being equal to h minus R4 sine theta 4, that's one expression, and underneath I go R5 cosine theta 5 being equal to x minus R4 cosine theta 4. So I have those equations now, like this was equation 1, so that's, if you like, 1 dash now, and this is 2 dash, just arranged it. Now, if I have this two equations, this set of two equations, how to get rid of theta 5. I want you to pay attention because this is something we're going to do a fair bit. So luckily I have now r5 sine, r5 cosine theta 5. I can like sort of square and add those terms. So I go r5 squared sine theta 5, sine squared theta 5, right? So plus r5 squared cosine squared theta 5 equal to h minus r4 sine theta 4, and you square that, plus x minus r4 cosine theta 4, and you square that. And in this case what I did, just saying square 1 dash square plus 2 dash square, right, and add, and this is what you get. Now obviously here, if you take r5 squared as a common factor, you have inside the brackets cosine squared plus sine squared, they add up to 1. So now I have r5 squared, and this way I have managed to get rid of theta 5, and that's, we use this technique a fair bit. Now now expand the other side. I have h squared, I have 2 r4 h, right, sine theta 4, and I have r4 squared sine squared theta 4, and also I have x squared, I have minus 2 r4 x cosine theta 4, and I have r4 squared sine square cosine square theta 4. So here this is cosine square theta 4, and then I add those together, and those, obviously those two terms, they're going to give me those two terms here. Those two terms, they would give me r4 squared when I add them. Okay, so I can do that now. So I have x squared, write this equation, and do x squared, right, minus 2 r4 cosine theta 4 times x. So now I'm trying to get a quadratic in x here. So, and then I'll have all those other terms. So I have plus h squared plus r4 squared minus r5 squared and minus 2 r4 h sine theta 4 is equal to 0. So now I have my quadratic, whereby all this will be c, this here is b, and you can solve to find two values for x. So you can solve to find two values for x, just going here you have minus b, so you get do r4 cosine theta 4 plus or minus, right, 4 r4 squared cosine squared theta 4, correct, minus 4 h squared plus r4 squared minus r5 squared minus 2r4h sine theta 4 over 2, and you'll find that this was 2, so we'll find that 2 cancels out, and you get an expression for x. So you get two expressions for x. So you get a solution. Of course, 100% over here, you should be able to simplify this further, because you have, this is r4 squared, and this here is r4 squared cosine squared, and those together will give you sine squared. So you can take common factors and simplify if you like, but I'm going to leave it here for you to simplify and just say we have two values for x. We have a plus value and a negative value for x, and like we have, you know, of course you can tell now that those two values for x will correspond to two possible assemblies of the linkage. So whether you can, so you have another assembly possibly would be on the other side of here. So this would possibly another assembly over here like that. So if you have this other assembly, of course, right, then the value of R5 will change and the range of quadrants will change. And then when you calculate R5 with this information, or possibly, I mean, you calculate theta 5. I'm talking about theta 5. When you calculate theta 5 at this point in time, you possibly just get it from x. You'll have, in this case, you get two values for theta 5, one from this expression and the other one from this other expression. So those two expressions. So you get an expression for sine theta 5, another one for cosine theta 5, and you find theta 5 by using the sine and cosine together in a tan 2 arrangement. So this, if you decide to go to calculate x first, which doesn't have theta 5, and then calculate theta 5 afterwards. And so that's not the nice thing about this last expression I got was just the possibility of getting this insight into the two possible configurations, two possible assemblies I have for the linkage. However, I could have stopped if this was an exam question or something like that, or I'm trying to just, I know I am having this one specific, dealing with this one specific design. I could have just stopped here if you like, and I could have drawn x against theta 2 and theta 5 against theta 2 and theta 4 against theta 2 and also R3 against theta 2. So now we have obtained x and theta 5 as well. So I mean the outcome of the analysis should be really like graphs, four graphs against theta 2. You should be able to draw all variables, theta 4, theta 5, x, and R3, right? Type thing. So this way you'd have done your position analysis. So far we used trig to find our position equations, but also we can use the vector methods. I'm going to introduce now here position analysis with vectors. So that's my topic here. And then in terms of vectors, we'll be able to have what they call loop closure equations, apply vectors, attach a vector to every link, and then add those vectors together in such a way that I will get equations, sufficient equations to calculate my unknowns for me. Like, all right, so like the unknowns here in this specific problem, remember the unknowns, like I had four unknowns, position of every vector is an unknown, of every link is an unknown, and even including the sliding link. Previously, or the examples we looked at previously here in the four buried chain, I had really two major unknowns I wanted to find with theta 3 and theta 4, the position of the links. Previously, my two unknowns in the previous lecture were like in the slider crank linkage. My two unknowns were the angle of the conrod phi and the position of the slider x. So I always have those unknowns, and I calculate or find equations for these unknowns in terms of the given input to the linkage. The same thing will apply when we do position analysis with vectors, because this is the main concept of position analysis. Just wanted to say, maybe give you some quick things. I mean, about vectors, you'd have already some like a good idea about vectors, but I would say a vector, just x and y here. If I say, let's say I have point A here and I have point B, and then I have a vector over here. I'm going to call this, for example, R A. Maybe you just capital R for vector, right? So I'm going to say this is RA, and so this vector RA, you can write the vector like that. So it has XA and maybe value YA, and you want to say it's XA, YA, right? And 0 if you write it in 3D, but also because due to 2D, I can write RA as XA and YA, right? So that's, if you like, that's Cartesian being X and Y, Cartesian way of presenting my vector. Right, that's correct. And then, all right, but I can also, being in a plane, I can utilize the fact that vector is in a plane and say, okay, I have an angle theta attached to the vector, and I say, okay, so the xa is the length. So if the length of this vector is equal to RA, if you like, the length RA, then it's RA cosine the angle theta, and YA is equal to the length sine the angle theta. So that's another way of presenting the sign of the Cartesian values in terms of the length of the vector and then the angle itself. So by the way, it's 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 really important that when you measure the angle of the vector, you measure it using the right hand rule from the x-axis. So you go from like imagine that the vector and x-axis intersect at a point, and then you go from the x-axis to the vector. Meaning, if this is my x-axis and this is my vector, this is x and this is a vector here, I'd go like that. And this will be my angle theta, right? It's not, I don't go over here. If I go over here, I might say minus whatever, but when you use vector methods, let's agree that all the angles of the vectors will be measured in this one direction type thing, like from it's really counterclockwise from the x-axis to the vector work, or sometimes you say this is right hand rule, and that's really important later on when we calculate the velocities, because such an angle, if it is increasing, I get positive velocity. If it is decreasing, I get a negative velocity. Positive velocity includes rotating in the counterclockwise direction. All right, so this is what I'm talking about here. So when we will maintain our convention, we'll be okay later on with velocity and with acceleration and so on. All right, so that's another way of representing my vector here. All right. Okay, can I say also that I can, instead of using Cartesian, when I look at this representation here, straight away I have values, I have like a length, and I have an angle. So I realize the vector in a plane lends itself to polar representation, like a line, a length, and an angle. So it's it's now much simpler to use polar representation and more compact. So in a polar representation, we say the vector RA is equal to, well, you can say that. You can say it's length RA and some angle theta. Right? When you look at this representation, you know it is RA cosine theta in the direction of X, right? In the direction of X, and RA sine theta in the direction of y. And because I don't want those to be added, I say x direction has a vector directed towards it. I call it the vector I, and the y direction has a little vector directly along it, call it a vector j, and then I multiply those values by I and j, so I make sure they don't add up algebraically, right? They are two different things and not added, okay? So, and the way we ensure people are not going to add those vectors is by multiplying every uh, component here by a unit vector in the direction of x and unit vector in the direction of y. So this is still a Cartesian. This is polar. This is still Cartesian. All right, so that's a representation of the vector. Now, I can also represent the vector using another method, which is a complex number method. So I can say, or complex number notation, if you like. So we can use complex number notation for vectors. Complex number notation. So I'll go RA. So here I do that. I say I have real, which is my x value, that's real, and instead of y, I'll call it, it's y really, we know it's y, but we call it in complex number notation, we call it the imaginary axis. So when we have a vector, point A, that's RA, length RA, angle theta, we can write it like that. We can say RA as a vector is equal to the length RA, and then we say EJ theta. So this specific representation is called Euler representation. It's Euler representation of the complex number. So as if now the imaginary axis will put a j on that, and the idea here is I don't want, again, because when I sort of expand this, I go, it's RA cosine theta and nothing there, and then I say RA sine theta, and I put j on top of, or on front of this. Just use a different color for the, I think will be better. So here, and j time thing. So this j is this j, and the idea of using j, it's a complex number operator, if you like. Well, it's mathematically it's square root of -1, but in our course, it's just a symbol, which means we cannot add the two values together type thing. So, right? So this means this is an x and y, they are not added algebraically, right? They added in such a way that will give us a value like a shape, if you like, which is a vector, right? So this is a vector is presented in our course. So this is what I am adopting in this course, this specific way of presenting the vectors. So that's the method I'm using for the vector. So I have a length and I have an angle for the vector. All right. Okay. Now I'll go back to what I had done previously. Like I'd drawn something here. Right. So I call this x and y. You call it real and imaginary. To me, they are the same thing. Right. They mean the same thing. So I have A and I have B, and I have this vector here, RA, and this vector here, RB. So this will be theta B, and this will be theta A, right? Then, so I have RA as a vector, is RA, AJ, theta A. Don't forget the way and the direction in which I measure my angle, right? It's very important to pay attention to this. From positive X to the vector, right hand rule or counterclockwise, and RB is RB and the angle theta B, right? So A to theta B. Now I want you to pay attention to the following. What is the difference between those two vectors and this third vector I'm adding here, right? I can call this R B relative to A. So this is the name of this vector, B relative to A, as if someone is standing here at A and looking at point B. So hence I say B relative to A, right? Type thing. So the naming has a convention. It's very important. I say B. The way you read it is very important as well. All right. So now that are the difference between RA and those are RA relative to B, and those other ones the difference is those other ones, I refer to them as absolute position vectors. Three of those vectors are position vectors because they determine for me the position of a point, except those red ones are absolute position vectors because they give me the vector with respect to the origin, right? So the origin is stationary, it doesn't go anywhere. So I have absolute information here on those positions. But from A to B, I call this a relative position vector. So RA, so I have here RA and RA and RB are absolute position vectors, but the other vector, which is R B relative to A, is a relative position vector. All right. So the difference will be important when we talk about the velocity later on, because if you differentiate the absolute position vector, you get the absolute velocity of a point. But if you differentiate the relative position vector, you get only the relative velocity of a point, or the velocity of a point relative to an observer at the other point. So that's not the actual velocity of the point, just an apparent velocity from the point of view of, of some observer. So there is a big difference in the meaning of the two vectors type thing. So two types of vectors, absolute position vector and a relative position vector. You need to be aware of those. I think I'll possibly just stop talking about vectors now. Later on, if we need to explain more things about vectors, I'll explain those. But at this point in time, I'm going to just give you an example on how to use vectors to do the position analysis. So one example here is my famous slider crank linkage. So now, because I'm using vector methods, I always need to specify my x direction, right? Y is not as important, so x is really important because I measured angles from my x direction. Then I have my points here, that's point A as before, and point B. Okay, so now, so that's the x axis. Now I wanted so we use the vectors to do the position analysis. That's a very important example because it gives us insight into this. Now I look for loops. So the password is loops, right? I need to add loops of vectors, right? Here I have one loop, right? That's a loop, all right? So every loop, let's look, let's see what this means. So I attach to every, so I try to find triangles of, or whatever shapes of vectors. Like I have now, like multi-sided shapes, normally triangles with vectors. So I have this length is R2. So this will be, this length is R2 and will be a vector. So I'm going to attach a vector here. I'm going to call this R2, vector R2. And this length R3, I'm going to attach a vector. I'm going to say this vector is R3, right? And I can have a vector which closes the loop for me. I can call this vector if you wanted R1 maybe. Okay, that's R1. All right, okay. So now I have a loop of vectors. And then when I add the vectors together in a loop, like when you add R2 plus R3, right, the sum is the vector which closes the loop for you. The sum is R1. All right, so straight away I have an equation. We'll explain this in detail in a little while, but I just wanted to say for every loop, I'll get an equation like that. So we'll call this the loop closure equation. If you want, just call it the loop equation, that's fine. The loop equation. So for every loop, I will have an equation. And then what will this equation give us? The equation will be able to give us, because it's a vector equation, I can resolve it into two linear equations, into two scalar equations, I meant to say. So those can be two scalar equations. So if I have two equations, I can find two unknowns. So this means every loop closure equation will be able to, will give me the opportunity to find expressions for two unknowns, right? So what are the unknowns I have in my uh, sort of linkage here? Don't forget I have x, this an unknown, this distance, right? Let's call it xb this time around. That's an unknown. And I have the angle of the link 3 is also an unknown. So I have two unknowns, and as a function of the input parameter, which will be theta 2, right? So I have two equations, then the two scalar equations, which I'll be able to get from the one uh, sort of loop equation, will be sufficient to perform the position analysis here and find my two unknowns. Now, let's set these vectors right and find the angles and do the angles of the vectors. Now, the first vector here, this one, and as agreed, I'll get the angle from the positive x and counterclockwise. This is my theta 2, right? How about theta 3? So, all right, so x doesn't intersect, like it's, link 3 at the origin of R3. So if I say take this as the origin of R3, I just imagine X goes at the origin, just to imagine that and to be able to determine my angle, right? So, and then we apply the rule right hand or counterclockwise. This will give me my theta 3. So this will be theta 3 of this link, right? And this over here, the angle will be 0, right, for R1. So let's write these vectors on the side here. So the vector R1 has a length which is xb, and it has an angle and goes above A to J, right? Remember the presentation? This how we present those vectors in the Euler method, right? So here the angle of R1 is 0, because R1 is always directed along the x direction. Okay, so R2, the angle length of R2 is R2, and the angle of that is theta 2. And then R3, the length is the constant R3, and then the angle is theta 3. So now I write my vectors in the polar form, and then I plug those in my equation here. So I go R2, which is R2 EJ theta 2, plus R3, which is R3 EJ theta 3, that's equal to R1, which is XB EJ0. So now I have my loop equation in a polar form. Loop equation in a polar form. So my procedure is quite systematic, and you apply for different linkages and so on, right? So I have this in a polar form. Then I break my equation, because it's a vector equation, I break it into the real and imaginary, right, directions. So, and I say, when I do real, the real on one side is equal to the real on the other side, correct? And the imaginary on one side will be equal to the imaginary on the other side. This is how I get my two scalar equations. So let's do that. So the real is R2 cosine theta 2 plus R3 cosine theta 3. The real is cosine. That's equal to XB cosine 0. And cosine 0 is equal to 1. So it's here I have R2 cosine theta 2 plus R3 cosine theta 3 is equal to XB. That's one equation, one scalar equation I got. Now let's do the imaginary. The imaginary is the sine thing. So I go R2 sine theta 2 plus R3 sine theta 3 is equal to XB sine 0, and sine 0 is equal to 0. So it's 0. That's my second equation. Now I have my two equations. If I want to get my XB, and I can possibly get rid of like what I did before now. So, and that's this systematic procedure with the vector analysis, I end up with equations that I solve together. All right. So over here, I can just simply, if I wanted, just put the cosine theta 3 on one side by itself. So I can say, okay, so R3 cosine theta 3 is equal to XB minus R2 cosine theta 2, and then R3 sine theta 3 is equal to minus R2 sine theta 2, and then I can, this is 1 dash and 2 dash, I can square and add to get rid of sine theta 3. So I can go 1 dash squared plus 2 dash squared. See what happens here. You'll end up with R3 squared being equal, when you sub and add, being equal to XB squared on this side minus 2 R2 XB cosine theta 2, and then plus R2 squared, right? And then when you sub and add, this is what you get. And then you have your XB squared being equal to, no, what I'm going to do is just arrange my equation, move my R3 squared to the other side, right? So minus 2 R2 cosine theta 2 times XB plus R2 squared minus R3 squared is equal to 0. That's a quadratic. In XB, I can just get XB as I did previously. So XB will be equal to, right, will be equal to R2 cosine theta 2 Here I'm just going to say find the roots or solve quadratics. Find the roots as before, and then will be x r2 squared, if you remember, plus or minus r3 squared inside here, 1 minus r2 over r3 all squared sine squared theta 2. This is x, and then I can plug x in equation 1 prime or 1 dash to find r3 theta. So r3 cosine theta 3 was equal to x minus that. So I can go, this is my x. All right, when you take this away, this part away, you end up only with the square root. So you can go, so that's, now this r3 is not squared, just realize, just r3 over here. So it's r3, right? So that's r3 into 1 minus r2 over r3 squared sine squared theta 2. And at this point in time, I can just simply just cancel r3 against r3 for on each side. So I can do that. So this gives me cosine theta 3, and then I have sine theta 3 was equal to minus r2 over r3 sine theta 2 sine theta 2. So that's what I had from previously, right? Don't forget that in the previous example, when we solved this with the trig, we're not finding theta 3, we're rather finding phi, the angle phi, right? Sort of not quite theta 3. They add up to some value, but they are not theta 3. All right. So once you have done that, you can find theta 3 from tan. So theta 3, you can use a tan 2 and use sine theta 3 and cosine theta 3, and you can plot again if theta 2, you plot xb and you plot theta 3, and you'd have done your analysis. Also, if you want to look at the expression that you get for sine theta 3 and make those conclusions that R2 will have to be less than R3, or the linkage is going to stall, and all those conclusions, the insights that you developed previously, you can still develop here as well, because you get the same sort of equations, but using a different method type thing. Let's look at another example, and this one I'm going to do the 4-body chain for you. So that's another example here. So I have a 4-body chain over here, and I wanted, so I have here a vector r1 and or length r1, sorry, r2, r3, r4, okay, and this gives me a loop, right? So I have the loop here. I can see the loop nicely. And all right, so how many unknowns? So one loop means 2 unknowns can be found, because I'll have 2 scalar equations. So my unknowns are obviously theta 3 of link 3 and theta 4 of link 4. The input, theta 2, is input. Those are my unknowns. So having one loop would make sense that I can find the 2 unknowns by solving the equations in the loop. However, this specific example will realize in a second that it's not as easy as the other one. Solution is quite involved to do this one. So I'm going to possibly move this to the next lecture and start the next lecture with solving this specific example and to show you some other mathematical tricks we can undertake when we solve uh, those equations which we get from the vector analysis together, right? All right, so please start do whatever as many examples as possible, as I always say, and if you get stuck, then drop us a line on Moodle or by email. Okay, thank you.